All right, let's get started. So may I have attention? Okay, so we are 5 minutes into the class already. So unfortunately, I forgot to bring the right dongle for the connection. So this particular one can only connect to my Mac. Therefore, I couldn't write anything, on the screen. But unfortunately, today's lecture needs some writing, unless you actually really can follow the slides without any derivation. So I'm going to clean up that part, in case we need any derivations, and hopefully you can just use this screen for the lecture purpose. So remember from last week, we covered the first topic on variational inferences. Anybody still remember what particular algorithm we talked about? Low-P belief propagation. And if any take-home message you get from that lecture, what is low-P BP after all? What is it is trying to solve? If you can summarize in a few words. It is a best free energy optimization, and in the space of some valid marginals, like singleton marginals, pairwise marginals, right? And we actually didn't have enough time to run into mean field. In fact, this weekend, after I go through the material, I decided to rearrange the order a little bit. We're going to push the mean field lecture this Wednesday, or maybe later this class. I'm going to actually begin by presenting the general theory of variational inference, in particular this so-called inner and outer approximation, which you actually heard a few words already in last classes. So you can see the whole thing in right context, and then we can inspire basically the mean field in a more natural way. So remember in the low-P belief propagation, basically we had there's no pen, so it's not very handy. But we are trying to turn the problem of approximate inference, into a optimization problem. Right? So that's the first thing. Inference become optimization, and then when we do optimization, we need to choose an objective. And I believe in there are many ways of defining the objective. Last time we were trying to basically defining the objective to be the free energy of the distribution, right? Which is a measure between the KL divergence between the true distribution and your approximating distribution. I want to minimize that. And then we say that, well, for an arbitrary complex approximation, computing that very objective, which is the Gibbs free energy, which actually includes a term that is an expectation of the potential function, if you remember, right? So if I remember correctly, this free energy has a term which is the expectation of all the potentials, right? And also of course, this is P, and here there is this entropy of the distribution, right? So this objective function itself is as hard as doing the whole inference problem if we were dealing with this true distribution. Then we said, well, what the belief propagation or low-P BP is actually doing is to seek an approximation of this, right? Where we replace this one with something that is only dependent on the pairwise marginal and the singleton marginal, and we replace this one with the so-called the best entropy, right? And if you don't remember the term, I think that slide is not on this particular laptop, but you can probably find out in your slides last time, right? It's basically something to do with the potential of P of xi and xj and the P of xi only. I think we call it B, the B message, right? And this one is basically the singleton entropy plus the pairwise entropy, and the singleton entropy, the singleton expectation is multiplied by a factor, which is what? The degree of that node minus 1, right? And this one is a pairwise line. And here we just compute the sum of the pairwise entropy and the singleton entropy, right? And that is the exact energy for what kind of graphical model, if you remember. If the graphical model is a tree, then that actually is the exact term by definition, because if you remember the junction tree definition of joint distribution, it is a bunch of pairwise terms on the denominator, on the numerator, and a bunch of singleton terms in the denominator, if you remember that, right? And then we say for arbitrary graphical model with loops and other things, we can just follow the same term as if they are a tree and then write it anyway, then we get an approximation. And we say that this approximation has certain properties, right? It's a closed form, but it is not necessarily a lower bound and so on. All right, so with all that today, I'm going to give you the more general theory about this whole practice called variational inference, so that hopefully what we've done so far is well inspired theoretically. So here is the roadmap. We're going to revisit these two families of approximate inference algorithms, low PBP and mean field. Okay, and also we're going to study the connection of these two, and then we're going to provide a unified view of what's actually going on. Okay, what's going on actually is a redefinition or relaxation of the objective, and also a relaxation of the optimization space. And you just want to now, be pre-warmed by these two terms. One is the outer approximation, the other is the inner, and you will see why it is called so. All right, so let's first get in touch with what is a variational method, okay, or variational principle. Anybody heard this term, variational calculus, or anything like that? Okay. If most of you haven't, then I don't want to really go through the whole math because it is a complicated one. I'm going to give you some very, very simple, operationally useful definition. We basically, okay, even my laser pointer isn't working, so this is a really tough situation. All right, so variational is a fancy name for the optimization-based formula, which is the following. So you are interested in certain quantity, say the likelihood of the data under distribution, or the marginal of something under distribution, and you want to make that particular quantity you are interested as the result of some optimization problem. Okay, so that's the first bit of message. And here is two examples. It's kind of tricky to make this a transformation, but I will give you just some well-known ones. For example, everybody know what is the eigenvalue of a matrix, right? So eigenvalue of a matrix can be computed by, well, in MATLAB, you just type eigen and you get everything, right? What is actually happening is a eigenvalue decomposition, and then using some linear algebraic routines. But you probably also know that this very definition of the eigenvalue can be also defined variationally. It is the solution of this maximization problem, maximizing this quadratic term over the space of unit vectors. Okay, and once you find the right unit vector, meaning in the right orientation, you do this quadratic calculation, you actually can compute the maximum eigenvalue. Okay, so that's one definition. Why it is fancy? We can stop asking at this point. We can find out later. There are many, many values for this definition instead of the MATLAB one. The second one actually is a little bit less obvious, but let's take a look. So this is a linear system, right? And A times X equals to B. A is a matrix, B is a vector, X is a vector. And let's assume that B is a positive semi-definite, okay, or positive definite maybe, even not semi-definite. And then this is invertible, therefore computing the solution is just a matrix inversion problem. Very, very clean, right? But for some reason, you could also view this as, there is no optimization here whatsoever involved, right? But this one, X star, can be viewed as the solution to a optimization problem, which is here, right? It is minimizing this quadratic term minus, this linear term. And the minimizer of this is your solution to here. Isn't that strange? Why this is the case? Can anybody see this particular case? Do you have like a 5-second derivation of this? Why these two problems are equivalent? Huh? All right, so just to give you a hint, so this quadratic term, if you want to minimize that, you need to take the derivative of that set to 0, right? And if you take the derivative of this with respect to x, in here you get ax, in here you get b, and that's exactly this condition. Okay, therefore this problem is the stationary point of this. This is actually, if you want to dig deeper, this is a convex problem. Therefore, its solution is at the stationary point, and the stationary point is actually defined by this condition. Therefore, the solution between these two are equivalent. But why this is interesting versus this? Well, in here you have to invert a matrix, and sometimes inverting a matrix isn't very fun, right? If you have a very big matrix, and in here you are having a optimization problem, and we know how to solve optimization problem in generic way, right? You just do gradient. You can do whatever gradient, conjugate gradient, coordinate gradient, everything. And therefore, you can start from a random guess and then iteratively just run a gradient update. You can still get a solution like this, right? Which involves no inversion, right? So that's kind of giving you an idea about why sometimes a redefinition based on the variational principle can be very interesting. And the kind of approximate inference procedure that you've seen so far and what we will be covering in a second is along this line. And in our case, of course, our quantity of interests are those probabilistic queries, right? And in particular, we might be interested. So this is a general definition of the graphical model, especially in a macro-random field. You can define directed one similarly, but the interesting quantity will be, say, marginal of certain subset of nodes, or maybe a singleton node. And the partition function. Partition function can be what? In many cases, partition function corresponds to the likelihood of data, right? Remember, if you do the Bayes rule, the conditional probability of some data given evidence is basically P of a joint divided by P of E, and this is the partition function, right, of the whole thing. So that gives you the likelihood. So computing Z in whatever context can be also interesting, and that's a typical inference task. So now we ask, can we turn the solution to these two problems as that of a optimization problem? Okay, so that's the goal of a variational inference. They don't need to be treated like this way, because here I already have a solution. You can do marginalization like this. Here, you can sum over all the configurations of X, you get that, right? So it's all doable in principle. But as we studied earlier, they are exponentially complicated, right? Sometimes you want to find a easier procedure, and that variational procedure could be easy if you do it right. So our goal is to come up with a generic formulation of this whole thing. Therefore, we're going to now use the tool from exponential family distribution and convex analysis to turn a problem around, so that our solution can be applied to general graphic models. That is falling into the definition of an exponential family. Okay. So we all know what is the exponential family already. Here is a very, very, very quick overview. It has canonical parameter theta. It has the sufficient statistics. In many cases, you design out the potential function. It has a log partition function, which is defined like this. By the way, log partition function is, by definition, convex, right? And you should be able to tell why it is convex by either checking the book or just derive by yourself. And then, just based on this definition, you can also come up with a domain of the theta, okay? Because the theta has to be such that they are valid. They are not going to be every possible theta. In what sense it is valid? Well, at least it should make sure this log partition function is legitimately defined. It should be a finite quantity. Otherwise, if this is infinite, then what's going to happen? The whole probability will become 0, right? So I have this very loose definition of the theta. It is everything that makes this finite. Okay, that's it. All right. So that's expanded family distribution, and the graphical model can be expressed as a instance of this kind of distribution by realizing that your potential function, okay, is actually the equivalent of this part, which is the canonical parameter times the sufficient statistic. In a sense, I'm implying that this particular expression, due to some array parameterization, can be written in a linear form, right? And then you have the z, which is the normalizer, and it is also a partition function. So here are just a few examples. We can go very quickly. We know that a Gaussian MRF, right, in the Gaussian Markov random field or Gaussian graphic model is a member of the exponential family distribution. Just by realizing this, right, you have now a quadratic term of the sufficient statistic and the linear term, not quadratic term, the sufficient statistic, and this is the coefficient matrix, right? And this one, correspond to two types of sufficient statistic. If you want to be very explicit, one is this singleton one, the other is a pairwise term, right? And this one, of course, corresponds to the entry in the covariance matrix. Not covariance, in the precision matrix, right? And so you have the natural parameterization plus the sufficient statistic. And of course, you need to notice that there is a structure correspondence that defines, makes sure it is a graphic model, because the zero and non-zero list in this matrix of coefficients indicates the presence and absence of an edge in this graphical model, right? So that's why you have this structural correspondence between the parameterization and the structure. And here is a discrete case where you can also introduce the parameters and the sufficient statistic as this. In this particular case, I only introduce one type of sufficient statistic, which is the indicator function of a particular node. And then we have both singleton potential, pairwise potential, and in this case, pairwise potential is just a product of the two singleton indicators. You can, of course, write a joint indicator if you wish to make the whole thing a little bit more expressive, but that's just a design of a different sufficient statistic. So this is meant to say that there is a kind of generic way of expressing probabilistic graphic models as members of the expanded family. And in the model of the expanded family, you have two key quantity. One is the natural parameter. The other is the sufficient statistic. Okay? And what's the inference problem here? The inference problem actually, corresponds very keenly to the form of the sufficient statistic. Why? If you remember our earlier lecture on the exponential family distribution, anybody still remember why we care about playing with the exponential family distribution? Remember anything from there? Why exponential family distribution is an interesting form to play with? Do I have it here? Oh, I have it here. Because there is a very simple mapping of the mean parameterization and the natural inference problem, right? So here, you have this mean parameterization mu, which is corresponding to actually the expectation of your sufficient statistic, right? And they correspond to what? The first derivative of the log partition function, if you remember, right? And here is another moment matching function, right? And also there is this nice correspondence between the partition function and the log normalizer. All right. So why actually we want to actually do the expose this? Because down the road, you are going to use all these identities to establish a very good, important connection between the canonical parameters and the mean parameters. Okay, how to establish that? So here we have a P, right? This is the expectation of the sufficiency statistic over the true distribution P. P is parameterized by the theta, the canonical parameter, right? And once you use that, take the expectation, you also get the estimation of the mean parameters. Okay. And we're going to use this on and on very regularly to make sure that you can now do the inference problem in two different spaces. One is in the natural parameter space, and the other is in the mean parameter space. So here, let me show you an example, okay, of such transformation between the mean parameter and the natural parameter, and how the variational principle actually play a role in getting the inference part quite easy. So we all know about the Bernoulli distribution, right? It's just a univariate binary probabilistic distribution, right? And one way to write that down is to write it in this way. I'm basically turning that into a instance of the exponential family distribution. How to get there? You should just know how to do that by going through the old slides I sent out. Right? There is a way to, cast every term in your empirical way of writing the distribution into this canonical form of the exponential distribution, where you have the coefficients, the sufficiency statistic, and other things. All right, so just make clear, we have the distribution like that, and the inference is about computing the mean parameter, because the mean parameter corresponds to computing the marginal distribution, right? Because in here, this is the mean parameter, and by definition, it is equal to taking the expectation of the sufficiency statistic. The sufficiency statistic itself is an indicator function. Therefore, this one corresponds to computing the marginal distribution of the one state, right? And then you actually can write it down like this, because everything over there can be written in closed form. You can just write down what is a P of x1, right? So you can see that between this mean parameter and this natural parameter, you have this very interesting relationship. It's a function there, okay? So that's all very easy. If we knew how to write down this already, we can write them in closed form. There is no, complete inference step. But still, I want to show you how to do the same thing using a variational principle, so that solving this problem is equivalent to solving a optimization problem. Okay. So what's this? Okay, so that's the slides I put on Windows, and now it is not behaving quite right to on the Mac. But I can draw the graph. Now I remember what it is. Okay, so let's first talk about a term called this conjugate dual function. Okay, for any function f. Okay, let's just draw an arbitrary f. So first, remember this Bernoulli distribution and our manipulation first, and keep it in your backyard, and we're going to revisit that because we already solved it using closed form derivation. But now I'm going to show you how to solve it in a variational form. So we have this arbitrary function. Say, okay, so f. Okay, I have this f function. Then I want to define a thing called it's a conjugate dual. Okay, it is defined just by this. It is a supremum of a linear term, theta times mu. Mu is theta is actually the argument in the original function. Mu is a new one, is a free parameter which is the argument in the dual function, and minus f of theta. So what does this mean? It is basically what is theta times mu? So this, for example, is a coordinate system, and the x coordinate is theta. And how does that first term look like in this graph? Isn't that like this? Just a straight line with a slope of mu, right? So that's basically this guy is basically by the way, this angular bracket is the physicist in the way of writing a dot product. Okay, so it's a dot product. So maybe I should just make this explicit. Okay, and then this first one minus the theta f theta is basically the distances between this guy and the other function, right? It could be here to here and so on. And I want the supreme of that, really the biggest distances. Okay, and you can just go home and convince yourself. Now I tell you the result where the distance, where that particular thing is. It should be basically, a curve that have the same slope of this one, but touch basically here. Okay. So basically here you can get the biggest distances between this and that. And for every mu, okay, suppose I have a different mu now. Okay, I will have a different touching point, which might be somewhere in here, and so on and so forth. Therefore, you have a function, okay, which is called the dual. And this function is, by the way, having some nice property. Actually, what I drew here is supposed to be here. You can hopefully find the prettier picture from the printouts. It is a convex function, okay, first of all. Why? Well, I kind of write the point here, right? Because it is really just a bunch of linear functions, right? Theta times mu. But it is a pointwise bundle of that because you are going to try over all the theta, or all the mu, okay? And a pointwise supremum of a class of linear functions, or linear a bunch of convex functions is by definition also convex. You can check that out from Boy's book or many other places. So that's one thing we want to remember. Every function has actually this fact is regardless of whether that f function is convex or not. Okay, f theta can be anything, but still its conjugate dual is a convex function. Why that's interesting? Now you can see that I'm turning an arbitrary function into a convex loss, okay, through some transformation. Okay, and so if the original f, is by itself also convex and lower continuous, this is the technical term to make sure they are differentiable, then the dual of the dual, you can actually go back, gives you this, okay, which means that you can also define the original function as the conjugate dual of the original function, okay, and all it manipulates is this guy, which is a quadratic, is a linear term, and then there is another function in here, which is either the original function or the dual function. Okay, why we do that? Well, the reason we want to do that is to allow you to realize this. You can actually now manipulate one of the inference tasks, which is the potential or the partition function of our distribution. Remember, one of the inference goal is to compute the partition function. Now it can be actually expressed as the supremum of this, which is meaning this one is the conjugate of that. Okay, and here the mu is basically an argument in here, and you can now call this a dual variable. Okay, that means you are basically hitting, you're throwing one stone at two birds. You solve this problem, which is one of the inference tasks, and as you get a solution, the argument also gets you the solution to the other inference problem, which is the mean parameterization. Okay, all right. So now let's see how it can be really used. Okay, so we have now the conjugate dual of. By the way, why this is true? This is just by definition. Okay, any function can be, whose their dual can be expressed in this. I just now introduce the function to be the partition function and its conjugate. So this is nothing special. What's special is the actual form of these two. whether they make the computation easy or not. And that's basically what we're going to examine here. Talk about, now going back to the Bernoulli distribution I just handled. Bernoulli is a closed form, can be expressed in a closed form with just one variable and one natural parameter and one mean parameter. And therefore, everything is actually quite easy. And we can see how the form actually switch back and forth in different transformations. Right? The first one is a statement of the conjugate. Okay, over there we have the original. Too bad I don't have a pen, but that one log of 1 plus exponential theta is the a theta, right, in the original distribution. That's the partition function. And then plus a linear term, and then take the supreme of that over theta, I get the conjugate, which is a function of the mu. Very interestingly, now it is a function of the mean parameter. Okay, and then we need to find the stationary condition that maximize this. Very easy. We take the derivative over mu for the thing on the right-hand side, right? Set it to 0, and this is our stationary condition. That gives you the explicit relationship between the solution mu to the original, canonical parameter theta. Okay, so that's by that fact. And obviously, once you have this, it makes you able to draw some important conclusion, because we first want to ask, is there a space or domain for mu that enable or ensure a legitimate solution, or are you unlimited? Well, once you solve that, you can go inside and probably realize that mu has to satisfy some conditions, right? For example, you can easily derive that the mu must be within 0 and 1. And if such thing is satisfied, then you can invert the function to get theta expressed as a function of mu, right? You could also say that I do this transformation first, and from here I get the conclusion that mu must satisfy something. But of course, in reality, you probably don't have that kind of luxury. You cannot do this transformation first. You need to first find, numerically how mu should be satisfied. And then if mu is out of that domain, then you have an invalid solution, right? And of course, in here, the conjugate dual of the partition function can also be expressed in a closed form. Okay. So in a nutshell, after all this, we have the following kind of conclusion, that the dual function, or in the dual space, can be written in this form, right? It takes this closed form as a function of the mu, and if mu is in the feasible space, and otherwise is going to lead you to an invalid solution. Okay. All right. So that's basically giving you an explicit variational form. It says that now you can solve the variational inference, the inference problem, which is to compute the partition function. Okay, using a argmax kind of a formulation, where you are going to take the max of here, okay, which involves the linear term and also the conjugate dual of the original problem, and then the mu must be in a solution space. Okay, and then once you have that, the optimum becomes very easy. You can get this by checking the stationary condition. So all looks very easy in this case, because you have the closed form everywhere. Right? For example, in here, this thing can be written in a closed form, as I wrote here, and even the A itself can be written in closed form. So you may wonder why we even need this equation. Right? Now the true challenge is that once we go out of control and have a complex graphical model where you have nothing in closed form but a symbolic representation of the experimental distribution, where you have the sufficient statistic and a bunch of natural parameters theta. And then you are asked to compute the actual value of A theta and the actual value of mu numerically, not in closed form, because you don't have a closed form solution to that. Okay. And then when you want to have a numerical answer, such a variational procedure is going to be very important because now you have the loss function and you can just solve a optimization problem numerically, okay, and get your solution in here and in here. Okay, so that's the high-level idea. And let's see what kind of difficulty we will run into. Yeah, so here is a high-level summary. Through a variational definition, we actually realized a few things. First, this is a dual function, or this is something I haven't mentioned yet. Okay, if you check the form of this dual function, this one, what does it look like? It looks like the entropy of the original distribution. And that actually observation should be extrapolated. Okay, it is true for every distribution. Okay, so that's one thing. And the second thing that it exposes you the feasible space of the mu. Okay, so that's going to be useful. So our next step is to develop this framework for the general exponential family distribution. Okay, and there we will have a few difficulties. One is that this conjugate dual, which is the entropy of the original distribution, is not easy to write. Right? You can write it symbolically, but you really cannot compute it. Therefore, that means that in your objective, there is a term you actually don't know what their value is. Okay? And the other is actually this constraint set, okay, which I showed you in here, appear to be quite naive. You can kind of see it from that. But in the real large-scale problem, setting that constraint set can be extremely non-trivial. Okay, and you will see a few examples. And then it is the compromise to these two difficulty that creates various different ways of performing variational inferences or production inferences. It's a quite fascinating story, but let's start from a generic look into such a transformation. So here, let's see how to compute the conjugate dual. We have a now general exponential family distribution, okay, and here we have a pi corresponding to the sufficient statistic, and the theta correspond to their corresponding natural canonical parameter. By the way, later on, yeah, so actually I'm going to express them, the first sum as use this, and in here theta is implicitly a vector, and this phi is implicitly also a vector of different potentials or different sufficient statistic. Okay, but by expansion you can make them into a d-dimensional summation because you have a d such sufficient statistic. And I want to now take a look about how their dual look like, because my goal, remember, is to compute the value of a theta and the value of all the mu's. Okay, mu, by the way, again, remember, is the expectation of every sufficient statistic. Okay, the mean parameters. Okay, so the roadmap is very easy, right? The roadmap is that you look at this dual function, you identify the stationary condition, and then you are going to now derive compute the derivative, in here using some closed form, and then this actually gives you the expected sufficient statistics. Therefore, at the stationary condition, you actually have this identity where mu equals to the expectation of the coefficients. Okay, so that is at the stationary condition, but it doesn't mean that you can actually compute it because this is a symbolic identity, and the computing expectation actually involves doing exact inference on the original graphic model, and the original graphic model is parameterized by theta. Okay, so in a sense, here you can have a hint now. So to define a feasible space of mu, how can we call the mu theta? Well, you first need to make sure that these are the mu's which are realizable by the distribution, parameterized by theta. In a sense, you can imagine such a thing. Suppose there is a space, okay, for the mu, and you don't know that, and then there is a space in here for theta. Okay, there is actually a one-to-one correspondence. Here, this one theta defines a particular distribution P, okay, And once you use that to compute all this expectation, it gives you actually one of the mu in here. There is this one-to-one correspondence. Okay, and our goal is to figure out how to use this one-to-one correspondence to identify the space of this mu, and also to see whether some numerical computation can be happening to allow us computing that mu in that space. Okay, clear about the bigger picture question? All right. So now let's see. Suppose that the solution of what I indicated earlier does exist. Okay, suppose this exists. Then you can pretty much plug in back the facts, and then get this mu replaced by this, and this derivation is meant to show that if everything goes well, that you have this one-to-one correspondence, and the mu is defined in the feasible space so that this mapping happens. And then your dual function, okay, is now an entropy of the original distribution. Okay, so that's the first thing. All these equivalents are not automatic unless you are in the right feasible space or constraint space of the mu parameters. And again, this one is not really computable if your distribution is very complex. So with all this, I want to wrap up with the few steps. Okay, so you start with this symbolic form of the conjugate dual, and you establish that this mu can be computed at the stationary condition, so that mu and theta establishes a one-to-one correspondence. And then using the theta, if that can be derived, you actually get a entropy of the original distribution, and that corresponds to the conjugate of the original distribution, of the original function. Okay. And okay, so now let's see how what kind of question actually we will run into if we want to use this principle to compute our mu parameters, the mu's and the a's. Okay. So here is one thing, right? We need to actually now really figure out, what this space is. Otherwise, this whole chain will break, because you cannot go from here to here if your mu is not solved in a correct constraint space. By the way, you look at here, you feel it's all solved, okay? Because all the equation goes through. This is not true, because these are symbolic solution. What you really need to deal with in the real computing will be the numbers. Okay, they don't remember equations. Therefore, you need to make sure that the mu has a number. Okay, then through some mapping, it gets you to the theta, and whether this number is obtained in the right space, we need to actually make sure of that. Therefore, we need to really ask what kind of mu, will allow us to have a solution of theta, so that we can have a solution to the dual space. And that basically is the variational inference problem. You want to solve this, query in the right feasible space based on some loss function, the objective. And remember, the objective is basically either the dual or the primal of the original partition function. And again, there is a complexity over there in terms of whether that loss function is definable or not. And we're going to tell that story in a second. So let's first worry about this feasible space of mu. This feasible space is a very interesting one. It is people figured out it due to the very definition of this mu, it must satisfy a condition called the marginal polytope. Okay, because of the following. So here, by definition, mu is the expectation of the sufficient statistic phi. Okay. And the expectation can be taken over any distribution. Okay. Therefore, the simplest way to define the space of that is it is such a mu that there exists a distribution, and the expectation taken according to distribution over the sufficient statistic gets you to the mu itself. Okay, so that's basically the definition of the space of mu. And this is, if you can try to visualize that, you may be able to realize that the space of mu is a convex set. Why? So here, this phi is what? Maybe I can show you even more so in here. So phi is basically a vector of what? Of sufficient statistic, right? And then phi is also a function of the random variable x. X, of course, is in the m-dimensional space, where your whole domain has m particular variables. Okay, so imagine the following. So I'm going to have this phi vector, and here are sufficient statistics of that. Just imagine I have xi, maybe xj, xi, and xj, and so on. I can invent many such sufficient statistics, right? But after all the the x, the entire collection of x. Remember, this is not sufficient statistics. These are my random variables. Is in the space of m-dimensional, right? And there are basically 2 to the m configurations of a x vector. 2 to the power of m many instances, right? Because I'm assuming every x to be a binary one, and there are m of them. So I'm going to have all these 2 to the power of m combinations of x value, and each of them basically gets you an instantiation of this sufficient statistic vector, right? And they are what? They are basically the points that must be included in the space of the M. They are called supports of M. And then what you have at the end of the day in here, you can see, is to sum over all this M thing, or 2 to the all these 2 to the M configurations with respect to their probability, right? So this is a weighted combination of all these vectors, or m such vectors, and a weighted combination of all the vectors creates a convex hull of such vectors. If you remember the basic principles in convex optimization, right? So therefore, this one is a convex hull of the sufficient statistic, and it is of course a convex set. Okay, so that's our first cut into how the feasible space should look like. The M or the mu should live in the space which is defined by the convex hull of the sufficient statistic. Okay, and that's a pretty difficult space, right? Because you have m such parameters, and therefore this convex hull is supported by at the corner by 2 to the power of m such points, like all these points. Okay, so that's one way of defining that, just to tell you how big the space or how complex space can be. Another way of defining that is to use this Minkowski-Wiles theorem, which basically says that any non-convex or non-empty convex polytope. By the way, this convex hull is in the form of a polytope, okay, because they are linear combinations of vectors. And so another way of representing the same thing is to use the so-called half space, okay, or some finite connection of linear inequalities in this form. Basically, this one you can imagine, for every one of these, each pair creates a half space, and therefore the M space should be on this side of this particular surface, and on this side of the surface. Therefore, if you put them all together, that defines the outer boundary of this convex Hall. And that's equivalent to defining a convex Hall in the linear combination way. Right? So here we have a different definition, which is the half-space representation. All right, so now we have two ways of defining our constraint space of the mules, but they are not very easy, right? I mean, this is quite abstract, especially in the high-dimensional space, and we can actually take an example in here. So suppose we have a very easy Ising model, just two variables, very, very easy. And now our sufficient statistic, by design, I want the sufficient statistic to be x1, x2, and x1, 2. That's it, okay? And then the corresponding mean parameter is the probability, marginal probability of x1, x2, or the pair, both being 1. That's the mean parameter. Of course, my goal is to estimate this. And my first goal is to figure out the feasible space or the constraint space of all these estimators. Okay, so that you can see now the problem already, gradually. And so let's figure out how the space look like. So we have now a sufficient statistic vector of a 3-dimensional. Okay, so that's basically so today's scriber should have a hard time in picking up all the notes, and I expect you to do that. Okay. But on the other hand, I'm going to slow myself down quite a bit because I need to wipe the board and write again. So take your time to copy the stuff. So I'm going to have this sufficient statistic vector, x1, x2, and x1, x2, right? And now, remember, I need to find the support of the convex Hall, okay? And that's by enumerating all the configurations of an X, right? So you can build a contingency table, x1, x2, and also x1, 1, 2. So you have a 1, 0, 0, and by definition, that pair sufficient statistic should be 0, right? And then I have 0, 1, and what is this? What is the third dimension? Also 0, because that by definition it equals to x1 times x2, right? Then 1, 0, 1, 1, right? So it is going to be the convex Hall of these 4 vectors, okay? Well, a convex Hall is easy to say, but it is numerically a little bit hard to enforce. You know, once you say my solution will be in this convex Hall, then mathematically, how do we enforce that? Well, this half-space definition makes things very handy. So here is the equivalent definition of that convex Hall, which becomes a little bit mysterious. Okay, so here are the 4 half-spaces I suggest, and you will be able to figure out whether they are reasonable or not. But in fact, I will tell you these 2 are equivalent. The first 3 I found to be quite intuitive, right? So this one is what? It tells you some basic. These are conditions coming from facts or simple derivations of the distribution, if you know it. If you know it, it will come up with this. That means that if the distribution is well-defined, it must satisfy such condition. For example, the marginal probability of x1 being on must be bigger than the joint probability of x1 is on and the x2 is on, right? And the same thing, marginal of 2 bigger than the joint of 1 and 2. And of course, the joint of both should be bigger than 0. It should have a bigger or equal to than 0. That's the definition of the probability. The last one is a little bit mysterious, right? Anybody want to give it a try? It took me a while to figure out because I forgot my earlier notes. How do you interpret this one? 1 minus the joint, 1 plus the joint is greater than a marginal plus another marginal. I can wipe the space for you if you want to do some quick derivations. Anybody see the intuition behind that constraint? Again, it is about a fact in such a probabilistic distribution of 2 random variables. Therefore, they are made as a constraint. If you don't even satisfy the fact, then the distribution must be invalid, right? So here is a less than straightforward fact, but let me go with a very quick derivation. So here is the whole space of the joint distribution. Let's imagine. Okay, remember our earlier tutorial of probability in 701, we used this kind of a Venn diagram thing. And suppose this is an event where x1 equals to 1, right? And we can also draw an event of x2 equals to 1, right? And it could be that these two things may overlap a little bit, right? Because these two events may be dependent, may be coupled. So there are some mass which is overlapping here. So, and what is this guy? This is the probability of x1 equals to 1 and x2 equals to 1, basically equals to mu 1, 2, right? So now you can see from there already, right? It basically says that if you add this and add that, you are basically adding this twice. You need to subtract this one, right? So basically mu 1 plus mu 2 subtract, and this mass should be smaller equal to 1, right? So that's another constraint we want to have. So as a result, now you have 4 extreme points, and the 4 half surfaces are sufficient. Therefore, you have this feasible space defined by all the half spaces. Now you actually at least know your solution space. Of course, for greater graphical models like 3 nodes, in fact, you will have 16 constraints, quite non-trivial to write down. And if you have a arbitrary graphic model, you are going to be crazy because a lot of such constraints, right? You really don't know, all these extreme points and polytopes will be very hard to visualize. So that's actually creating you the need of the so-called variational principle, right? So our high-level picture is that using all these, facts between the primal and the dual of the inference problem, and also some facts satisfied in here, we have the following master equation for variational inference, in which the partition function is the supreme of the linear term, the mean parameter, the natural mean, the canonical parameter times the mean parameter minus the dual of the partition function, which is the entropy, and the space is the so-called marginal polytope. And I wish I could write here, this one you cannot do it, and that one you cannot do it, right? Therefore, this symbolically very clean operator problem is actually quite hard for arbitrary graphic model. But nevertheless, it does turn the original inference problem into a optimization problem. That's the good part. Okay, so the rest of the literature in the variational inference is actually about how to manipulate these two parts. Turn this into an easier form, turn this into an easier form. Therefore, I'm still solving a optimization problem, but with hopefully controlled approximation, but with a lot easier computational step. Okay, and again, I want to emphasize that if the solution is made correct, then there is this one-to-one correspondence between the sigma, the theta, and the mu, so that you can have this very nice, unique kind of mapping between the two space. Okay, clear about that? And I believe now we are ready to throw in some more examples. Which slide I'm at? I'm at 23. Okay. All right. So so this is a 2-node Ising model, and we already played that quite a bit. And now we can pretty much copy things down, right? We can write down this canonical form, this dual form, and which is the entropy, right? And in fact, you can plug in the definition, and you will be able to hopefully arrive at this very expression of the entropy function. Okay, and even from here, you already can see the constraint. Of course, here you are talking, a loopy story. You already know this. If that, then you can also derive the constraint in here to make them feasible. But what I did before was more like a first principle approach without looking at the solution. Okay, and then your solution to the partition function will be a maximization over that, okay, and in the space defined by that. And at the end of the day, you get this, okay, in this case, a closed form, okay. If everything like this can happen for all graphical model, then you don't need to learn what I'm talking about, because closed form is just too easy to be, too good to be true for arbitrary graphical model, right? So what you really want is to start even from here, and with here, this term being replaced by some easier one, with this one being replaced by some easier one, then you do numerical optimization instead of a closed form derivation. Okay, so that's the key message. All right, so with that, let's restate the variational principle in here, and then we're going to start our endeavor of how to actually instantiate the approximation algorithms. The original slice was meant to tell the mean field first and the BP second. I'm going to reverse the order because we already learned BP. So now I'm going to bring you back, the BP in this context so that you understand it. Then we're going to talk about the mean field if we have time, and then all the way connects to the next lecture, which we're going to expand the mean field into fancy models like topic models. Okay, right. So let me stop here and try jump ahead a few slices. Well, I hope you find this decision better than just going to the mean field, because you haven't heard about mean field yet, at least in the clean form. So let's revisit this whole thing, right? This one we know that already, right? So let's see how does this story fit into what we just talked about. A lot of equations, but don't be intimidated because you've seen that already. I'm going to just gently restate it, right? You have this message passing thing, and you derive the marginal like this, and this algorithm is exact on trace. That's all we know about the BP, the sum product algorithm. And what is in here? Oh, yeah, so I typed the right thing on my PC, but here it still did not go well. So this is, you should put a summation sign in here, sum over all the nodes, and sum over all the edges. That's it. This is just a general definition in the exponential representation for a arbitrary tree graphical model with singleton potential and pairwise potentials. Okay? And the sufficient statistic is defined as those indicating the states of a singleton or a pair. And your mean parameter is basically the marginal probability of a singleton and a pair. That's basically your inference task. So your goal is to compute these two mean parameters. Okay? And yeah, that's basically the definition of all that. So these are also clear. And now, okay, so here we need to decide on something. What is the marginal polytope of the tree? Okay? Marginal polytope means that where is the feasible space of those mu, so that all these are guaranteed. Always all the P, will leads you to a marginal of the thing that you actually inferred about. Okay, so this is not very easy to actually describe, but let's do a leap of faith. We know that by the junction tree property and the marginal, that if you know how to infer that, must satisfy the local consistency property, right? They should be self-normalizable. They should be marginalizable to the shared nodes, right? These are called local consistency. Then by leap of faith, we know that local consistency also leads to global consistency. Therefore, this definition is sufficient to define the entire valid distributions on tree, right? So that's basically how we, draw, a simple definition of the marginal polytope. We didn't actually work it out explicitly, but we indirectly using the junction tree theorem to convince us that this local consistency is good enough to define the whole space. All right, so that's basically our feasible space is done, and then we need to worry about the loss function, right? The loss function, remember, is if you remember the variational principle, you have the linear term, theta times mu, and the A star, which is the entropy of the distribution, right? And on tree, we actually know how to compute the entropy, right? You can do it in closed form. And that's the definition here. You see singleton entropy. You see this KL, between the singleton and the marginal and the pairwise. And at the end of the day, you have this closed form definition, okay, which are all computable based on just the mu's, that you're going to derive, right? And so we have now a clean objective, and what you do is to solve this, optimization problem. You have a dual function, which is defined, in closed form. You have the feasible space. Yeah, so this is unfortunate, but you can see that the feasible space is due to the singleton constraint and the marginal and a local consistency property. And then you have the Lagrangian. This is the loss, and these are the constraints. And solving the Lagrangian is by taking derivative of the loss with respect to the arguments, right? And then you have now these two solutions, which we showed you last time that they correspond to messages, right, in the graphic model. Right, so that's basically some product algorithm on a tree graphic model. And the moral here is that on the tree graphic model, we have everything under control. Okay, basically, this guy is under control because we know how to compute entropy on tree. And this guy is under control because we know how to define the marginal polytope on trees. Okay. And the story goes to out of control when we have an arbitrary graphic model where we cannot compute the entropy and also the marginal polytope. Right? And that's where, by the way, this is the restatement of the message passing. We actually see that before. So now let's see arbitrary graph. On arbitrary graph, this guy cannot be expressed in closed form, and that guy cannot be expressed in closed form either. And therefore, we introduce two approximations. Right? The first approximation is that we claim, even though we don't know the M exactly, we're going to just use that local consistency inspired by tree to define a space for the mu. Okay? And this space is called an outer bound of the feasible space. Why? Why it is called outer bound? Well, you actually let me actually show you the graph before I can tell you why it's the outer space, because it's more easily visible geometrically. And then for this guy, which we also don't know how to compute, we're going to replace them with the best free energy, right? And that's basically the loopy bit propagation. Once you have these two in place, you are going to now do message passing just by introducing these constraints over this loss, and then you have a loopy BP algorithm. Okay? And now let's see why it is called a marginal polytope, called an outer bound. Well, first of all, we realize that this one, L of G, is not the same as the M of J, right? Why? Because it is defined only on local consistency, and in the arbitrary graphic model, local consistency does not necessarily lead to global consistency. Okay? So therefore, in that space, there are more distributions which may be invalid in the original sense. And that's why this whole thing is bigger than the M. It must be bigger because there are some tau which cannot be in M. Okay? It's not valid. But on the other hand, if you look at the support, the corner of the original marginal polytope, they must be all actually in the L. Okay, because you can test, just by bringing, the expectation over every sufficient statistic, and you will find that they are legally defined. Therefore, it is basically also here. Okay, and in fact, they are also the corner of that space. And therefore, if it is, sharing the corner but bigger than that, you basically are drawing the outer bound of the original marginal polytope. Okay. So that's basically an approximation. You are going to be optimizing your problem in an outer space of the original constraint, which gives you some trouble because you may end up with a solution in here that is not valid in the original distribution, but still valid in your current solution optimization problem. That's why we say the loop PPP may not be correct. Okay, and of course we also talk about this approximation to the loss function, which we said before, right in here, right in that one. So that this double hedge approach to a variational definition of inference leads to the loop PPD propagation. Please remember that. And the key things is that the best free energy replace the true entropy function, and then the outer bound of the marginal polytope replace the marginal polytope. And just for fun, you can throw in some examples for this 4-node graphic model, and you will be able to find that this pair of things is actually valid in your designed model, but you will see that their best free energy and their true best entropy and the true entropy actually produces very different numbers. Okay, this one, for example, gives you a negative entropy, and this one gives you something completely different. So that's why this best solution is potentially inexact. All right, so now we actually have another 5 minutes. I can say a few words about the mean field. And that one could be made a lot easier. So we said that the holy grail is to now somehow turn this problem easy. And in the loop PPP, we are changing A and M. Okay. So the idea behind mean field is going to be also changing this and that, but actually we are going to change this only, not that. Okay. And here is the idea. So one of the reasons that this A star, which is the entropy of the distribution, is hard to compute is because that P distribution is too complicated. Or in another word, this mean space, the parameterization space, is too big. It realizes any distribution, therefore any valid distribution on the graphic model, therefore it is complicated. So a different idea that we can explore is to look at the so-called tractable subgraphs. Okay. For example, here you have a graphic model which is realized by such a full space of parameterization. Okay, meaning that any edge can be non-zero. But what if I'm going to constrain myself to be a factored graph? Okay, I'm going to remove all the edges. This is an approximation called omega of f0, in which I have a constraint that the theta over st, which is the edge in the original graph model, to be forced into 0. Therefore, I only have this empty graph, or not empty graph, no edge graph, disconnected graph. That's one approximation. And another one could be I'm going to only allow some edges, which makes a tree, but no other edges. Okay, so in these cases, the omega are made smaller. And remember, the omega, I don't have the graph anymore. Remember, I have this little drawing. I have this marginal polytope M, and then I have this space omega, and they have this one-to-one mapping, right? Now, if I carve this to be smaller, in that I'm also constraining this space to be smaller, right? So that's the intuition. I'm going to now constrain my M, the marginal polytope, okay, so that the distribution that I'm going to manipulate is going to be a easier one than the original one, such as these two. And as a result of that, you actually get a lot of benefit. Okay, so first of all, this will be for some theta in the original space. Okay, and I call them an inner approximation. And again, the reason can be explained later. But the greatest advantage is that now, with this inner approximation to the feasible space, suddenly I can compute this potential or this entropy function. Okay, this entropy function now is computed on the subspace of all possible distributions, and they are sometimes called the simple distribution. Therefore, it is the exact dual function, but restricted to a subspace. Get confused? A little bit confusing now. So in the best free energy, we say that this guy cannot be computed, we approximate it with a best entropy. Okay. In this case, we say we're going to first limit my space into a subspace so that we only deal with easier distribution, and therefore this term now can be computed. Okay. So therefore, this term is actually an exact term. That's why variational inference based on mean field has a nice property, because it has the nice lower bound, upper bound property with respect to likelihood, because they are exact, but they are going to give you a smaller solution space in terms of feasible distributions. Okay, that means some of the right distribution is not realizable. On the other hand, in the BP approach, you have a outer approximation. So in theory, all the right distribution are realizable, but they are not realized because here you have an approximation term. Your target is wrong, in a sense. Right? So that's the kind of two flavors in variational inferences. And so let me just show you one particular example. In here, if you put the whole thing into something called a mean field approximation, where we only care about a distribution where the true distribution x, okay, now becomes a product of p of xi, just multiplied by singleton marginal. And then this is an extremely simple distribution, right? Originally, your entropy of p is not computable for this generic joint distribution, but now the entropy for this guy, how to compute that? Just sum of individual singleton entropy, right? Therefore, this term over there can be computed. This term, yeah. So it can be easily computed, and therefore you can solve the problem in that space. So next class, I'm going to talk about this mean field strategy for a number of model instances. It is perhaps by far the most frequently used variational inference procedure across all graphic models, just because it's so easy and it is convergent, although quality-wise, we don't know, but it's operationally very easy. Okay. All right, go home and read the assigned material for topic models. That's probably one of the highlights in the class. Everybody wants to know topic model, right? So you're going to read the paper, and then I'm going to cover the inference procedure in next class. Okay. Sorry for that ugly writing.